let's do an example problem where we calculate the solar energy resource, the total amount of solar energy that is impacting the Earth, and compare it to the total amount of energy used by people. So the annual energy consumption of all humans on the planet is E sub people is about 480 quads. That's 480 times 10 to the 15 BTUs, British thermal units. Let's convert that to units that we're more comfortable with. 1 kilowatt-hour is equal to 3,409 BTUs. So that's our unit conversion factor. So the energy consumption, and this is, I should have said this when I first wrote it, in 1 year. It's the amount of energy used by people in 1 year. It doesn't mean anything to just throw that number out there without saying how long it takes for people to use that much energy. So that's the annual, I guess I said annual, so that takes care of the in 1 year part. So let's just convert the units. The way we do our unit conversion, we take our original number, 480 times 10 to the 15 BTUs, and then I multiply by units conversion factor. I want to replace the BTUs with kilowatt hours, so I use this equation here. I'm going to put one of those numbers in the numerator of this conversion factor, the other in the denominator. I'm going to do it in such a way that the units that I want to go away cancel out. That means putting 3409 BTUs in the denominator, and that means 1 kilowatt hour goes in the numerator. So then that gives me the energy for people equals 1.4 times 10, 1.41 times 10 to the 14 kilowatt hours. That's the amount of energy used by people in all forms, not just electrical. Amount of energy used by people in a year. And now let's compare it to the energy of all sunlight hitting the surface of the Earth in 1 year. So we're going to remove the 25 or so percent, 25, 30% of the solar energy that's coming in that is reflected or absorbed by the atmosphere, and only count the part that comes in to the surface of the Earth, and we'll call that E solar for 1 year. So we're going to add that up, and to do that, we're going to have to work from what we know about sunlight is the solar constant is the power or the flux of solar energy coming from the sun. So remember the relationship between energy, power, and time. Energy equals power times time. So the power of the sunlight is 1,360 watts per square meter out in space, but because some of that is absorbed in the atmosphere, we're just going to use our number of 1,000 watts per square meter at the surface of the Earth. And because that's per area, I'm going to need to multiply it by an area. Of course, the time that we're dealing with is 1 year, and we'll be converting that to hours. So the area that I've got that sunlight is hitting is pi times RE squared, where RE is the radius of the Earth. So we'll look up the radius of the Earth and calculate the area that's absorbing that sunlight. And we get that R sub E is 6.37 times 10 to the 6 meters. So that gives me an area of pi times 6.37 times 10 to the 6 meters squared, or an area of 1.27 times 10 to the 14 square meters. So I can now calculate the total amount of energy that comes from the sun and reaches the surface of the Earth in a year is 1,000 watts per square meter times my area, which was 1.27 times 10 to the 14 square meters, times 1 year. And I'm going to have to figure out how many hours are in a year so that I end up with kilowatt hours for energy. But let's do things one step at a time. So E solar, 1,000 times 1.27 times 10 to the 14, meter squares cancel there. It's just 1.27 times 10 to the 17 watts times a year. And the number of hours in a year is 24 times 365. And that gives me hours. So I have E solar equals 1.11 times 10 to the 21 watt hours, or 1.11 times 10 to the 18 kilowatt hours. Converting from watts to kilowatts, I divide by 1,000 because there are 1,000 watts in a kilowatt. So now let's compare that to the number of the amount of energy that we had used by people, and we can see that is our use number 1.4 times 10 to the 14, and our flow value is 1.1 times 10 to the 18. So E people was 1.4 times 10 to the 14 kilowatt hours. So if I take the ratio of those two numbers, I will find E solar divided by E people is 1.1 over 1.4 times 10 to the fourth. And we've done some approximations here. 1.1 over 1.4 is about 0.7. Not going to worry about that little difference. It's on the order of magnitude of 10 to the fourth, which is 10,000. In other words, the flow of solar energy hitting the surface of the Earth, if I had not done that correction for the Earth's atmosphere, this 1.1 probably would have been a little bit bigger than 1.4, so a little bit less. Ballpark 10,000 times greater than all energy used by all people in every form. In other words, I only need to capture 1/100th of 1% of the solar energy hitting the Earth. If I can convert 1/100th of 1% of that solar energy into the kinds of energy I use, I'm done. I don't need anything else. Now, of course, our conversions require devices that are not 100% efficient. So we need a capturing area that's bigger than 1/10,000th of the cross section of the Earth if we were really going to do this to produce all our energy. At the same time, we don't need to use solar to produce all of our energy because we're getting some energy for free from other sources such as wind. So this just gives you an idea of the magnitude of the solar energy resource. It is by far more than enough to supply all of humanity's energy needs.